Good evening, students. Today we are going to discuss an important topic in grade 11 chemistry, structure of atom, quantum numbers. Before we start to know what is meant by quantum numbers, let us see if you are identifying the position of, let us say, a person A. Fine. How do you identify the position of a person A? First, let us say the person is in the continent Asia, in the country India, in the state Tamil Nadu, in the city Coimbatore, and let us say he is in an area called Pyramid. So in that, a school called Bridgewoods Public School, in that grade 11, in the first bench he is sitting at first position. So this we can say the position of a person A like this. So we come from the higher area, that is the continent, to the particular place where he sits. Similarly, if you want to locate the position of an electron, there also we have certain numbers which are known as quantum numbers. So there are four types of quantum numbers. First one is N, which is known as principal quantum number. Second one is L, which is known as azimuthal quantum number. Third one is M, magnetic quantum number. And the last one represented as S, and we call it as spin quantum number. So these are the four quantum numbers which will represent the position of an electron. In short, let us see what does this principal quantum number represent. The principal quantum number represents the shells. Azimuthal quantum number represents the subshells of an atom, and magnetic quantum number represents the orientation. In other words, we can say that orbitals. So shells, subshells, orbitals, and the last one will indicate the spin of an electron. So this is a summary about your types of quantum numbers. Now let us see one by one. First one, principal quantum number, represented by small n, and it will indicate about the shells. Now let us write natural number. So it is being represented by natural numbers, that is nothing but 1, 2, 3, 4 and so on. If I write n is equal to 1, it is represented by capital K. If n is equal to 2, it is represented by L, n3 capital M, n4 capital N, and so on. If it proceeds, you will get like this. After KL Mn, generally we discuss about KL Mn, and this particular principal quantum number was given by Niels Bohr. So in Bohr's atomic model, you have seen KL Mn shells. Now if it extends, we get KL, Mn, OP and so on. Now let us write a simple structure of this. At the center you have nucleus. Now if you consider, these are the shells. This is n is equal to 1, this is n is equal to 3, and now n4, n5 and so on. The designation L, that is KL, M, N, O and so on. Now this principal quantum number, what does it represent? Number 1, it will represent the energy. So how you calculate the energy of this shell? En is equal to minus 1312 into Z square by N square kilojoule per mole. So using this formula you can calculate the energy of a particular shell. For example, if you want a K, so we can write like this: energy of K E1 is equal to minus 1312 into, if it is for hydrogen, Z is 1, so N is 1. So nothing but you will get minus 1312 kilojoule per mole. So this is the first advantage of principal quantum number. You can know the shells, and in that shells what is the energy of a particular shell, you can calculate using this formula. Now second one, you can also find the radius of a shell, nothing but size of a shell. Formula is Rn is equal to 0.529 into n square by z angstrom unit. Using this formula you can find the radius of any shell. Later, while discussing the numericals, we can calculate both energy as well as the radius of a particular shell. Now let us move to the second one, azimuthal quantum number. Now second one is azimuthal quantum number or subsidiary quantum number or secondary quantum number. This is represented by small letter L and it shows the subshells. There are 4 types of subshells: SPDF, and we got these 4 subshells from these words, that is spiral gave S, principal P, and from diffused term we got a D subshell, and from fundamental term we got F subshell. Now let us see. Sommerfeld has given this quantum numbers, and you can use whole numbers to represent this. That is from 0 it starts, 0, 1, 2, 3, 4, and the last one will be n minus 1. So where n is nothing but principal quantum number. How to calculate that? For shells, let us see. First one K, we know n is 1. Therefore L is equal to n minus 1, nothing but 1 minus 1, which is 0. So therefore in the first shell we can say that the L value will be 0. So finally we can say that in the case of S, the value is 0. Second one, if you take L, n is equal to 2. So L values will be 0 and 1. You know that it starts from 0 and the next one will be n minus 1, which is nothing but 2 minus 1, and that is 1. Hope you are able to understand. I am just writing 0 and then the last one will be n minus 1. So now if you take for P, the value of L is 1. Next, if you take M, where n is equal to 3, so what are the 3 values? 0, 1 and 2. Now if you are writing D orbital or D subshell, it will indicate the value is 2. Now the last one, if you take N, the value of principal quantum number is 4. Therefore, what are the 4 values of L? You know that it starts from 0. So 0, 1, 2 and 3. Now 3 represents value of L as 3. So SPDF can be represented, that is subshells are represented by azimuthal quantum number 0, 1, 2 and 3. Now if you write here, it is very simple. This is nothing but 1s. This is 2s and 2p, 3s, 3p, 3d, this is 4s, 4p, 4d and 4f. Hope you are able to understand this. Now the number of subshells in n is equal to 1 is 1, here it is 2. What are the 2 subshells? 2s and 2p. N is equal to 3, you have got 3 subshells, that is 3s, 3p, 3d, and n is equal to 4, you got 4 number of subshells, that is 4s, 4p, 4d and 4f. Now very important thing, remember this: if L is 0, it is S. If L is 1, P subshell, L is 2, D subshell, and L is 3, it is F subshell. Now let us see, there is one formula to calculate the value of L, that is nothing but orbital angular momentum. When you are calculating this orbital angular momentum, that is L, it is nothing but h by 2 pi into root of L into L plus 1. While calculating the numericals, if they ask you calculate the orbital angular momentum for L value, that is 1, then we use this formula. So hope you are able to understand. Now let us move to the next quantum number, that is magnetic quantum number. Now the third quantum number, magnetic quantum number, which is represented as M or ms. So it was discovered by Landé, and you know we are using integers for using the magnetic quantum numbers. So plus 0 and minus 1. So it will indicate the orientation of orbitals in space. What do you mean by orientation here? To explain that, let us take S and P orbitals. So this is known as S subshell. The shape is spherical. Now if you are taking the S subshell and you have a strong magnetic field, what happens to this? In the presence of strong magnetic field, the subshell gets oriented on the three axes X, Y and Z axis. Due to this orientation, now you call it as S orbital. And you know the definition of orbital? That is the probability of finding the electron is maximum. So we can write it as the maximum probability. The maximum probability of an electron. So it's a three-dimensional structure where you can find the electron. Now let us see. This is P subshell and the shape is dumbbell shape. The same way, if a strong magnetic field is applied, now what happens? This again gets oriented, so we can see that X, Y and Z axis are there. So three types of orientation is possible. So let me draw the axis first. So we have X, Y and Z axis. What will happen in the presence of a strong magnetic field? Now it gets oriented. So how? First one, the orientation is present on x-axis. Therefore you represent it as px. Now this is called as px orbital. I think you are able to understand the difference. Subshell does not have any orientation, no axis here, but in the presence of strong magnetic field, it is oriented on x-axis, hence you call it as px orbital. So you can find the electron here. So the probability of finding electron is maximum, hence you call it as an orbital. Which orbital? Px orbital. Next, second possibility is you have the orientation on y-axis, hence it is called as py orbital. Now the last one is if the orientation is on z-axis, you call it as pz orbital. So like this you are having three types of orbitals. So using this magnetic quantum number, we can represent the orientation of these orbitals in space. Now let us see how to calculate the values here. See, we got a formula that is m is equal to 2l plus 1. This will give you the total number of orbitals. Okay, so the formula gives you total number of orbitals. Let us say for n is equal to 1, that is, you know that it is k shell. For k shell n is equal to 1, and let us write down the values of L, that is you have 0, nothing but 1s. In this 1s subshell, how to calculate the value of m? So m is equal to 2 into 0 plus 1, that is 1. So you have only one orbital that can be written like this in a box diagram. You show it as 1s, and what is the value of m here? M can be 0. So you can say m is equal to 0, then it is 1s. Next, if n is equal to 2, value of n2 we can represent as L. Now the values of 0 and 1. For azimuthal quantum number you have 0 and 1, nothing but this is 2s and this is 2p. What are the values here? If at all you are taking L is equal to 0, now m becomes 2 into 0 plus 1, that is nothing but 1. There is one orbital, so you can write like this, nothing but 2s. Now because integers, right, this is 0, plus and minus. For that reason, the first value is always 0. That's why I told here m value is 0. But number of orbitals are 1, which is calculated using this formula. Now here also the first value is 0. Now if you take 2p, if L is equal to 1, the value of m is equal to 2 into 1 plus 1, that is equal to 3. So there are 3 orbitals. We can write like this. These are the 3 orbitals. Now what will be the values here? It will be 0, plus 1 and minus 1. So m values are plus 1, 0 and minus 1. The name of the orbitals are px, py and pz. You can also represent as p plus 1, p0 and p minus 1. So any representation is possible. So hope you are able to understand. Now let me show one more example. If n is equal to 3, the shell is m, values of L are 0, 1 and 2. This is nothing but 3s, 3p and 3d. Let me write for only this. So m is equal to 2 into L value is 2. So therefore you are having 5 number of orbitals. What are the 5 orbitals? We already know that it is dxy, dyz, dzx, dx square y square and dz square. Because you are in third shell, you can write n value as 3. Now what are the values of m here? At the center you write 0, here it is plus 1, plus 2, this is minus 1 and minus 2. So hope you are able to understand. So using this method, you can calculate the orientation of orbitals in the space, and the values also you can easily calculate by m is equal to 2l plus 1. Hope you have understood. Now let us move to spin quantum number. Now the fourth quantum number, that is spin quantum number. It was given by Goudsmit and Uhlenbeck. So the final quantum number indicates the spin of an electron. So let us take, you are having 2 electrons in each orbital. So one electron, if it is spinning in the clockwise direction, so as clock has this type of spin, so we have minute and hour hand spinning in this direction. If at all it is clockwise spin, you represent it as plus half. So here you are using the real numbers. That is nothing but a fraction, either plus half or minus half. The electron, if it is spinning in the clockwise direction, you use it as plus half, and also write an arrow mark in the upward direction. So it is full arrow mark, or you can also write half arrow mark in the upward direction. Now the second electron in every orbital will have anti-clockwise spin in this direction, and you use minus half for that, or arrow mark in the downward direction. You can also write half arrow mark like this. Let us take an example. In 1s, you have to fill 2 electrons. The first one is written in the upward direction, second one is written in the downward direction. So this particular electron has spin quantum number plus half, and this electron will have minus half. So what does it indicate? It indicates that it has clockwise spin, and the second one is having anti-clockwise spin. Similarly, you take 2p, in that you are having 3 orbitals, 2px, 2py and 2pz. Let us say According to Hund's rule of maximum multiplicity, we already learned that first you have to half fill this. So all the three are representing plus half, that means clockwise spin. Now the next three you will write like this. They are all showing minus half, that is anti-clockwise direction they are spinning. Hope you are able to understand. Using this particular quantum numbers, we can identify the size, shape, radius, energy and orientation as well as spin of the electrons. Next class we will discuss about the numericals based on quantum numbers. Hope you have understood this. Thank you so much.